Hi, everyone, and welcome to Backer Breaks It Down. In this episode, we continue working with exponential functions. This time, we're going to focus on something called constant percent rate. So anything that grows or decays at a constant percentage rate can be modeled by an exponential function. Okay, so here are the rules for what you do when you are given a percentage. Okay, so exponential growth, if you're looking at this formula here, it does say the same thing as our previous function formula we're working with that looked like this. Y equals A times B to the X power. Says exactly that. So P sub 0, that's your A value. And then B, they just have a special rule for B because we're talking about a problem where I'm given a percent rate. And so when it comes to what is B, what is my growth factor, I can find B by calculating 1 plus R. Now, when we're working with percentages, you will need to first turn your percentage into a decimal and then add 1, okay? Now, if I wanted to go backwards, if I were given the function and I was asked what is the rate, what is that percent rate, I'm going to calculate base minus 1 times 100%. Exponential decay can be represented with this function here, where P sub 0, that's your A value, and 1 minus R is your decay factor. The decay rate is found the same way as the growth rate by going base minus 1 times 100%. This will result in a negative. Simply ignore the negative. So in these problems here, it says determine the growth and decay factors and or the growth or decay rates written as a percent in the following tables, okay? So first thing, row 1, I'm given 2.9%. This is a rate. In order to find the growth factor, I need to use the formula 1 plus R, okay? So remember, we must first convert 2.9% into a decimal. This would be 0.029. I basically take the existing decimal point and move it 2 to the left. So my growth factor, my B value, is going to be equal to 1 plus that. So if I were to go 0.29 plus 1, right, I would get 1.029. Now to go backwards, okay, like I'm given a growth factor of 2.23. So to come up with the corresponding growth rate, I'm going to use the formula base minus 1 times 100%. Okay, so basically I'm looking at 2.23 minus 1 times 100%, and I end up with 123%. So why don't you pause the video and try the remaining 2 problems here for growth, and then we'll take a look at decay. So how did you do? For 34%, you should have gotten a growth factor of 1.34. And for 1.0002, you should have gotten a growth rate of 0.02%. So let's talk decay, okay? So I'm given a decay rate of 68%. I must first convert this into a decimal, move the existing decimal point 2 to the left, so I'm looking at 0.68. To get the corresponding decay factor, I need to calculate 1 minus R, okay? So if I go 1 minus 0.68, I get a decay factor of 0.32, and that would be the B value in my exponential function. Now to go backwards, okay, I have a decay factor of 0.953. To find the corresponding decay rate, I need to go base minus 1 times 100%. Keeping in mind, this will result in a negative number. I'll just ignore it. So if I go base minus 1 times 100%, I'm going to get a negative value. I'm ignoring that. because my percentage should be a positive number. So we're looking at 4.7%, but I'm ignoring the negative when I write my answer down. So why don't you try the remaining two? Pause, and then check back in. Okay, so for 19.7%, you should have gotten a decay factor of 0.803. You would have gone 1 minus 0.197 in order to get that. For the decay factor of 0.9948, you want to go base minus 1 times 100%. You would have gotten 0.52%. So now let's analyze some exponential functions. In these two problems, this is tell whether the population models exponential growth or exponential decay, then find the growth rate or decay rate. So what do we think about San Jose that has a population of 898,759 times 1.0064 to the t power? So my base is telling me that this is growth because it's bigger than 1. To get the rate, I'm going to go base minus 1 times 100%. Okay, so if I go that number minus 1 times 100%, I'm going to end up with 0.64% as my growth rate. When it comes to Detroit, we have the function 1,203,368 times 0.9858 to the t power. My b value is less than 1, which makes it decay. To find the rate, I'm going to go base minus 1 times 100%. So I'm going 0.9858 minus 1 times 100%. This will be negative. Simply ignore the negative. So we're looking at a rate of 1.42%. So exponential functions is anything that grows or decays at a constant percentage rate can be represented with an exponential function. When it comes to what is b, turn that percent rate into a decimal, right? Move it to the left. And then your growth factor is equal to 1 plus r. And if it's decay, your decay factor is 1 minus r. To go backwards and analyze an exponential function, you can calculate the percent rate by going base minus 1 times 100%. And that's how Backer breaks it down.